We just have to wait a second while it connects, and then we'll get this show on the road. Okay. Hello to everybody on YouTube as well now. And then we'll get this show on the road. Sorry, I had to. Good. Okay. So, ladies and gentlemen, welcome to this week's Monsoon seminar. Thank you for joining us. If you are listening to this and you haven't got an email from me recently telling you that which connection to use, you should send me your email and I will be able to send you updates and new links every week. As you probably figured out by now, every week is a different Zoom connection. So you either have to check the website or ask me to send you the link, or both. But let me just say, if you have questions on the talk, please put it into the chat and I'll call on you at the end to give you, either you can give your question live to the speaker, or I will read the question for you if you're feeling coy. In any case, let me move on. So the speaker this week is Beth Christensen from Rowan University in New Jersey, and she's going to be talking to us about Australia's connection and contribution to the Asian monsoon. Can I also ask you to mute yourselves and turn off your video to save the bandwidth while this is going on? You can turn it back on again at the end. Thank you. Beth, take it away, please.
Thank you, Peter. So this is really exciting. It's a great opportunity to share with the global community what we've been working on with respect to the Australian connection to the Asian monsoon. I've listed a lot of the collaborators that have been engaged in this project, but of course, I see the downside to doing updates at midnight, which is that I managed to delete a row or two. But it's those folks that I accidentally deleted appear here. They're the co-authors on the GRL paper that I'm going to be focusing on for the first half of the talk. That was published in 2017. And since then, we've had a lot of updates by folks who were on the expedition, as well as these folks in particular who are on the expedition, and many others. So I'll be, excuse me, bringing in some conversation about those updates as well. So you'll see these names throughout the talk. Of course, we wanted to say thank you for the money and the funding. Primarily, this work was supported by a USIP PEA award and also a DAAD award to go to Marham to work with David de Vliechauer and Jeroen Groeneveld. So what I'm going to do is talk first a little bit about the Asian-Australian monsoon system and link it up with ocean drilling, and then move into our work trying to understand the evolution of the modern Australian monsoon system. And talk then about some of our works in progress, which really are about how complex the Indian Ocean circulation is. This seems to be related to the motion of Australia, both the evolution of the modern monsoon system and these new kind of features that we're beginning to understand, such as the Tasman leakage. And then I'll talk a bit about where to go from here. And the thought of someday getting into the lab and doing data analysis again. So when you say monsoon, people tend to think of the Asian system. But of course, there is the Australian system, which is in the southern hemisphere. These two interact, built around the ITCZ, the Intertropical Convergence Zone. And monsoons in general, as you know, operate because of a pressure differential between a low pressure hot continent and a relatively cooler high pressure ocean system. And so the northern hemisphere Asian monsoon operates in the summer when the ITCZ has moved to the north, and the southern hemisphere Australian monsoon operates when the ITCZ has moved south. And so this coupled system, you can actually think of a bit as sort of a monsoon sandwich with the ITCZ right? Being the middle of this massive system. But of course, it's a lot larger on the top end because we've got both the Indian and the East Asian systems working kind of in tandem and in complement to the Australian system. Now there's another element that is shown really nicely in this diagram from Wang et al., which by the way shows low-level winds and the precipitation fields, and that is the Western North Pacific. And so again, the monsoon is driven by that pressure differential, and so you kind of have to consider the ocean to be a little bit of the prize, so round out the whole system. So the precipitation that arises, the pressure differential between the land and the sea leads to precipitation, which of course I have to complete the analogy with our friend the beer. But as many of us know, you can have too much of a good thing. And so while monsoons bring vital moisture and rains to these regions, what we're seeing lately is that we're getting too much. Precipitation has increased and it is predicted to continue to increase into the future. And so really understanding what drives the monsoon, the relationship to the ocean system, the continental system, and the timing especially, what drives the timing is really important. It is literally life and death in some of these places. So much of this phase of ocean drilling, IODP2, or International Ocean Discovery Program, was really dedicated to understanding the Asian-Australian monsoon system. And so here, this is actually an image from the first regional synthesis workshop that was led by Peter and his gang, listed there. In 2017, shows the distribution of these legs. And the one I was on and the one I'll be talking about is Expedition 356. I'm also showing the Western Pacific Warm Pole Expedition 363, which at this time was still kind of being completed, and the Tasman Frontier, which has been drilled since then. These all provide critical information to understand the Asian-Australian monsoon system. You see the blue boxes on the left here, right, fall really neatly into those major precipitation zones identified in the model of Wang et al. And so it's almost like it was planned, right? Couple of weeks ago, hopefully you saw Steve Gallagher give a really nice overview of the Australian monsoon and climate evolution. He mentioned some of the work that we've been doing from Expedition 356, so I'm going to be expanding on that now. And it also, this work that I'm going to talk about today touches on so many of these expeditions. And so it illustrates how important this regional approach has really been to unraveling or I wouldn't even say we understand, but getting closer to understanding some of these major questions. I'll also pull in some of the legacy of ocean drilling, which is DSDP and ODP. I will, however, be giving you sort of the Reader's Digest version of the 2017 paper as well as the updates. So I would encourage you to please refer to the original works. So here's some photographs of Expedition 356. We focused on the western coast of Australia. We had some really wonderful wildlife sightings. It's a great place to work. It's always nice when all that time at sea is interrupted by some cute little critters. And I'm going to be focusing on site U1463. Now this figure shows a lot, but primarily what you should be pulling from this is the dynamics of the Australian monsoon system. So on the left, we have winter conditions when it's dry. And you see that it's dominated in the northern part of Australia. by winds that blow across, the trade winds that blow across Australia. So it's not able to bring much moisture into the interior or to the northwest. Instead, it transports dust. And the background diagram here is the percentage of C4 plants. And you see, as you might know, it's probably not a surprise that C4 plants dominate this region. You'll also note site 763 is nearby. That also falls under this dust transport pathway. Take a look at the summer, January, right? Southern Hemisphere summer, and the ITCZ has shifted farther south, bringing those monsoon rains to this region and allowing for the rivers to flow and often flood. And so what we have here is a representation of the two proxies that we can use to reconstruct climatic conditions in this region: dust and fluvial transport. So Expedition 356 drilled 3 good holes. So it's another attempt, not so good. The expedition, as I said, is focused here along the western margin of Australia. And that's pretty much concurrent with the position of the Lewin current. Now, the Lewin current flows from Indonesian Throughflow region, outflow region, south, bringing those warm waters poleward. And it kind of squeaks in between the Western Australian current, bringing cold waters north, and the continent itself. I have to say thank goodness for our co-chiefs. They appreciate and love logs. So each of these sites was logged. And that's really important because those logs give us a way to, a framework to compare the sites. We were able to work really quickly after we got off the ship with the log data. And since that time, we've been filling in the research that we did and the inferences that we made from the logs with more time-consuming foraminiferal and other sedimentological data. So I'll be focusing on site U1463, as I said, shown here. We published this in GRL in 2017. There's been a lot of work following up from this. Of course, another important paper that came out around that same time was led by Jeroen Groeneveld on the Miocene. He's going to be talking about that in December, so I'll put it on your calendars. But I'll also be talking about updates to the work at 1463 by many of these co-authors, as well as some additional folks that have joined our group. And one of those papers also pulls in 1459. And we just saw a paper that came out a couple of weeks ago by he et al. On U1461. You'll see 762 and 763 mentioned. These are ODP cores that are found farther offshore in the Exmouth Plateau. All right, so here's a photograph of a 1463 core 13H, and you see it as that beautiful green. And so we have a lot of excellent outer shelf upper bathyal sediments. Seems a little confusing because when you look at the site today, here, it's in 145 meters of water, and that's generally not associated with this kind of sediment. But we have a unique condition here, and that's been described by Mike Gurnis and Michelle Clements and Steve Gallagher, and that is reversible subsidence, or negative uplift, as we like to call it. The bottom literally drops out of the Carnarvon and the Roebuck basins up here, somewhere between 6 and 5 million. We have 300 meters of subsidence, and then it pops back up in the Pleistocene. It's a very, very strange phenomenon, and it's unexplained. So a lot of opportunity to collaborate with the neotectonics folks in your department there. But the upshot is that we have about 5 million years of that beautiful green, right? This excellent outer shelf, upper bathyal reservoir for marine sediments, as well as the continental sediments. So thinking back to that diagram of the monsoon system in Australia, we've got both the dust and the rivers that are flowing to our location. Whoops, I'm carried away there. Let's see if I can go back. Nope, I'm not even going to try. And those sediments are there and available for analysis. Now, as I said, we logged all of these sites. And so the NGR, or natural gamma radiation logs, come in 3 flavors or 3 colors. If you look at this map, this is the radiometric map of Australia. And this is published by Geoscience Australia. And what it shows is the distribution on the surface of the radiometric elements. Potassium is shown in red, uranium in blue, and green is thorium. And you'll see the location of U1463, and the big orange arrow shows the approximate position of the dust pathway. I think I broke it. All right, here we go. All right, so if you look at the data discretely, the Nakamura 2015 data, you see that the percent of potassium is higher, a deeper red on the left around fluvial systems, and it's the thorium potassium is higher, the red on the right, underneath the dust pathway. And so this sets us up to use potassium as a humidity indicator. Okay? And what you see here for U1463 is a plot of percent K from 6 million to a little under 1. And you see that the Pliocene, we have a couple of patterns here. The first is that we have a really rapid onset at 5.5 million. And it persists for a couple of million years until around 3.3 million. The use of potassium as a humidity indicator here is supported by the association with abundance of illite, as weight percent illite. These were discrete samples that were taken. Okay, but I'll get back to this later. The timing of this onset has been updated by Boris Karatsolis. Sorry about butchering your name, Boris. Similarly, the thorium potassium record allows us to look at aridity. And so aridity, thorium potassium here is being used as an aridity indicator. Thorium potassium is associated with heavy minerals. Studies link thorium logs with heavy minerals. The heavy minerals have been shown to be present in aeolian transport in this region. And what we also did was ran a kaolinite-illite clay ratio to make sure that the variation in the thorium potassium is not being driven by the clay assemblage, i.e. the K part of this log. And so we begin to see a change in the character of the thorium potassium log at about 3.3 million. And that's really an amplitude change. But at 2.4, we see a really high, much higher frequency change. And so we interpret that 3.3 million as the start of a change or a transition to a more arid environment, and 2.4 is the onset of the aridity. Again, that timing has been updated, and I will be talking about that in a few minutes. Uranium is also really abundant at the surface here. Right? And so uranium is also associated with heavy minerals. And in this location, not universally, but for this location, we propose uranium as a proxy for aeolian transport. And you see it really nicely coming on at 2.4. So when we put all of this together, you see we have the thorium potassium log. It's plotted with the ETP behind it in gray. We have the uranium, right, dry in this direction, and the percent potassium dry in this direction. Plus, we've plotted next to it some work by Cyrus Karras et al., 2011 B, the ODP site 763A temperature record from the Exmouth Plateau, and the LRO4 global splice, or global stack. So when you put this all together, you see that we have this rapid onset at 5.5 million to a humid interval, or an interval where we have abundant precipitation. This is coincident as well with a high sea surface temperature at the Exmouth Plateau. I think I broke it again. There we go. And this is a time period where Australian humidity is high, and it is also a time period where the Pacific meridional gradients have expanded and the ITF is wide open. So we have easy exchange from the Pacific to the Indian, and the waters themselves, 763, so the Indian as well as the Pacific, are quite warm. That changes at about 3.3. Okay? We've called this our transition interval. And the most important thing to recognize here is that it is not coincident with the onset of Northern Hemisphere glaciation. It occurs well before that and ends well after that. But this is characterized by a reduction in the percent K, a change in the character of thorium potassium, as well as a drop in the sea surface temperatures at Exmouth Plateau. Sorry, that was fast. We change at 2.4 into the arid interval, and there's a lot going on here. The percent potassium is at its lowest, uranium, ppm, is at its highest, and the thorium potassium is, we see a high frequency variation here. We are interpreting this as the onset of the Northwest Dust Pathway, 2.4. And if you look at the thorium potassium record, you see behind it again the ETP. This is a period, excuse me, which has a positive correlation between ETP and the thorium potassium. And what that means is that we have an enhanced seasonality at this point. And so this time period, we step into at 2.4, a period very much like our modern monsoon, or modern Australian monsoon. So what's driving this? The answer to that question is the Indonesian throughflow and changes in the Indonesian throughflow. Excuse me. So Australia has been moving progressively north throughout the Cenozoic and also progressively restricting the ITF. And this is important because it's important for the story about aridity and what's going on in the ITF, but we'll see later that it's actually serving as a gateway for the Southern Ocean and Indian Ocean circulation around the southern part of Australia. As Australia moved north, it directly influenced the regional and global climate by gradually uplifting the maritime continent, or that set of land masses just north of Australia. And in turn, that constriction impacted Australian climate and probably African climate as well. So on the left, you see a diagram, a plan view, excuse me, of ITF, of the Indonesian throughflows from Gordon 2005. And as Australia moved north, it changed the configuration of land masses and the pathway for Pacific Ocean through the Indonesian Throughflow. And on the right, you see how that change occurred. This is a diagram from Molnar and Krohn in 2015. At the top, it shows modern distribution of the land within the Indonesian Throughflow. And in the bottom, in red, it shows what portions were probably not emerged 5 million years ago. Okay? And so the difference basically between the lower panel and the upper panel is what drove Indonesian throughflow, or sorry, is what drove Australian aridity. How? Well, Kane and Molnar and Cronin predicted that what would happen is the tropical Pacific waters that were flowing through the Indonesian throughflow would be cut off and instead replaced by North Pacific waters, somewhere in that interval between 5 and 0. And so Cyrus Karras and his group worked to document that. And they were able to do so with records from the surface as well as the subsurface. And I've shown you a little bit of that, and I'll show a little bit more now. So our study steps in to connect the dots, to elucidate the very close relationship between those marine records and the Northwest Australian climate record. And then the subsequent studies have really stepped in to refine the timing of the change within the ITF. So here we have those data that I was just mentioning. Here we have the Eastern Indian Ocean. You've seen this already. Okay, but what you haven't seen is the Site 214 data, the central equatorial, and this is the subsurface, crassiformis, and the surface waters, as well as the Western equatorial Indian. Okay, so this work, of course, could not have we wouldn't have been able to understand the driving force without all of this previous works by Karras et al. And so what we see is that change begins in the transition zone, right? We're calling it starting around 3.3. I've highlighted broadly that 3.3 zone. And we see that the subsurface waters begin to freshen and cool in this time period, this little interruption and change at 3.2 or so. And the surface waters at 763 also begin to cool. This might delete. Right? And then at 2.4, we see that full onset of the dust pathway, but we really don't see a huge change in the marine records. Our timing for the increase in aridity in Australia matches really nicely with the terrestrial vegetation records. This is from Andreas et al. 2018. You see that we begin to see a change at 3.3 in yellow, transition, and then full on dominance of C4 by 2.4. We also see change in Africa. We see a drying in East Africa that's recorded in the leaf wax and hominin tooth enamel plus pollen. This is work by Lydia et al. And again, I've highlighted our transition point in yellow. So this is really holding nicely around the basin. And one of the things that I was really happy to see, and personally, this is a nice way to circle back to work that I did about 20 years ago with Mark Maslin on Leg 175. We edited a special issue of the Journal of Human Evolution, trying to unite the paleoanthropological community and the climate community to look at really the connection between climate and evolution. And this is a diagram of our cousins from the Smithsonian. And you see that there's some innovation at 3.3, but a lot of innovation around 2.4. And so you know, we'll just leave it at that. I think it's pretty exciting to be able to come back to this. Now, updates to the timing. The onset of the human interval. It is probably not as dramatic as the %K leads us to believe, right? So Boris Karatsolis looked at both the 1463 and the 1464 records. They're in different basins, Northern Carnarvon and Roebuck Basin. And what he found is that that substance that I told you about, that 300 meters of reversible substance, was differential across those basins. And so that differential substance manages to obscure the earlier humidity record at 1463. And so most likely this region was humid by at least 6 million. And this makes a lot more sense because it's concordant with the work that Holborn et al. Did to show that there was a southerly shift in the ITCZ around 7 million. A major innovation in our understanding of this region has come from Becky Smith's record. She published that in 2020. There's a lot to it. I don't have time to explain it, but I will point out, it's shown here, that she sees some changes in the SST that could lead us to want to extend the transition to about 3.1 MA. This is a big drop in SST. You know, but again, we have some continental and we have some marine records and a little bit of difference there. And unraveling that is going to be really fun. The arid interval holds with her work, but within that arid interval, she finds a really strong SST cooling, 1.7 to 1.5 MA. And there's also been some work investigating the stratigraphy at site 762, one of those two slightly more offshore sites. And after some back and forth, we're able to show that the modern monsoon in the Northwest Australian system is still coming in after INHG. It is not controlled by the Northern Hemisphere glaciation. These updates are also showing us that the ITF was pretty complicated and that, as you would expect, that constriction did not occur all at one point, and that it's probably occurring in pulses. So David de Vlieshauer published a refinement to the timing. Right? Gerald Auer looked at the North Pacific, the switch using nanofossil assemblages, and he was able to pinpoint that at 3.54. David Ben and Alfredo Garcia, Martinez Garcia looked at U1459 as well, and they inferred some reorganization that starts as early as 3.7, and they really highlight the role that the ITF played in sea level played in the MIS 2.2. And then, as I said, we end up with the highest SST cooling from 1.7 to 1.5. So there's a lot going on in the ITF, and it's not a simple on-off, but in Northwest Australia, the aridity seems to be, it begins to feel that around 3.3 and then really kicks on at 2.4. Hot off the presses, as I said, recent work from site U1461, a little bit more to the south, also holds for those three, the timing of those three intervals, but he sees an increase in SST at 1.2 MA, which is pretty cool too. All right, so our work at using the logs and those updates make it really clear that the climate of Northwest Australia plus the regional oceanography is not controlled by the Northern Hemisphere system. And what we suggest in that paper is that the Southern Hemisphere oceans were coupled and working, of course, within the global system, but not directed by the Northern Hemisphere. And since we said that, we found support for that idea in the idea of the Southern Hemisphere supergiant. Now this is shown here on the right. It's a model from Schweik et al. That shows that the Southern Hemisphere oceans connect both at the surface, shown in red, through the ITF, but also at intermediate depths, shown in yellow, through the Tasman outflow or the Tasman leakage. I'll talk about that in a minute. Over here, you can see a work by Ridgway and Dunn, a little too complicated to go into, but what they were able to show was that you can trace this connectivity between these Southern Hemisphere water masses on salinity. Right, so the modeled supergyre is supported by observational data, and what this all says to me is that Australia is serving both as the switchboard at the ITF, but also as a gateway for Tasman leakage. Right, so this is my really, I don't know, I would say bad attempt at visually presenting Southern Hemisphere circulation. I didn't even put the Northern Hemisphere on here. And what I want you to note is the ITF and Tasman leakage in yellow. This is intermediate level, but also these ocean drilling sites. And so I'll be returning to these in a few minutes. Note too, that the Tasman leakage is an intermediate source, but so is the green. That's an AAIW source coming directly off of the ACC. Go back to the Miocene. In contrast to the modern, you don't see, or we don't have that Tasman influence. We have the open ITF. It's not restricted yet, so it's not affecting the aridity of Australia in the same way as it did starting at 3.3, but we don't see that Tasman leakage. The continent of Australia is too far south, plus the subtropical front and the circulation is just not allowing waters to move around the southern part of Australia. But that all changes at 7 million, and I'll show you this data in a second. 7 million marks the onset of Tasman leakage and an intermediate water exchange between the Pacific and the Indian. So what is Tasman leakage? It's shown visually here. This is from Bostock et al. 2013. And it's basically East Australian current thermocline waters that mix a bit with some of the AIWs, but she's labeled it Tasman AIW, but this is Tasman leakage. And here, this is documented, or this is a model by Eric Van Sebeel et al. In 2014 that shows its distribution and transport. And so it's a fairly robust feature that we didn't know about. So as I said, Van Sebeel has done a really nice job modeling it. The green blob here is it shows the position of the Tasman leakage at different crossings. It's from 180 east to 95 east. And it's discrete, and it's centered around 800 to 1,000 meters of water depth. So what we wanted to do was try and find it in the sedimentary record, and we were able to do that using DSDP and ODP cores. We found it, but we found it at low resolution. So that's good that we found it. It's bad that we're kind of limited in what we can learn from it. So these are the Tasman, these are the sites that we are using to trace Tasman leakage. In green, all right, that's the pathway that has been, that Van Sebeel as well as some observational studies have shown that it takes around the Tasman Plateau and over to the Broken Ridge. So we got a site, DSDP site 590, Jim Kennett, 1986, and Broken Ridge sites from Ray et al. Are here. And we plotted the Delta 13C of Cibicidoides species, right? These are published data from those sites. You see that these two independent records converge at 7 million. So before 7 million, DSDP is picking up a Coral Sea record, and 752 is picking up an AAIW record. But at 7 million, Australia is far enough north to allow that water to flow around the southern portion of Australia. And this is supported by some radiolarian abundance data from Diesterhaus, albeit at a much deeper site at surface water. The Antarctic intermediate water sites, we're using Kerguelen Plateau, 751, and 90 East Ridge, 757. The 751 record is from Mackinson. As you might imagine, it's not continuous, right? Darn Southern Ocean records, but they track each other, right? So this is our pure AAIW signal. And when you put this all together, you see that they diverge at 750, at 7 million. So 752, 754, our Broken Ridge sites diverge from our AAIW sites at 7 million. So we have the Coral Sea and the Broken Ridge converging, and that unit diverging from AAIW. So this is our onset of Tasman leakage. And it works really nicely with some float data that Wang in 2005 analyzed. And she showed that there are basically two AAIW pathways, not knowing that what's shown in aqua there, the longer AAIW pathway, is actually Tasman leakage. So that's constrained to the east of 90 East, and then the AIW pathway is to the west, or modeled to the west of 90 East. What's really interesting is that when you start to look at sites around the Indian Ocean, there is a concurrent, this is a time period of erosion at many locations, at the Great Australian Bight, at the Marion Plateau, at the Maldives, and even the Florida Straits. So we're working with Christian Betzler and Gregor Eberle to put this together and see if what we're seeing here is evidence of increased circulation in the Indian Ocean at this time. So the Tasman Frontier results will be interesting as well. And so one more thing to consider. Now that we know that there was so much going on at 7 million, we wanted to take a look at an earlier study by Dickens and Owen in 1999, and some other references for this as well, that found OMZ-like conditions at the Broken Ridge, 752, 754. Remember that, right? They see a really dramatic dip in MNSC, which have been used to identify OMZ in the rock record. Not so much at 757. Right? And so the way they explained this was that there was a 5,000 kilometer extension from the OMZ to Broken Ridge. And that's hard to reconcile now that with this idea of an invigorated circulation at 7 million. Plus the fact that the Broken Ridge and the 90 East records aren't really the same. And 90 East isn't picking it up as much, although it should because it's north of the Broken Ridge. So I took a little deeper dive into the circulation of the Indian Ocean. And this is from Tally 2013. And this is kind of the thermohaline circulation pattern that we're used to thinking about. Right, where you have NADW, it comes up and returns, then the waters are coming into the Indian Basin as AIW. And if you pull out just the Indian Ocean circulation, you don't worry about the Southern Ocean, right? You can refine it to this idea of NADW sinking and Indian deep water or Pacific deep water, depends on your basin, is flowing up and returning as tropical or subtropical ocean waters. Right? And so that tells us that, and we can see here that much of the Indian Ocean is IDW, which is low oxygen, high nutrient old water. And the core of that is shown in this red line here, right? Coming up over here. So it's a low oxygen system. And here's the really interesting thing about the IDW. When you look at where what its role in the Southern Ocean is, you see this little blow up, it's the northernmost water mass, or the northernmost portion of the Antarctic Circumpolar Current. And so IDW arises in the most northerly fashion. And so this is the waters that feed the subtropic and feed the surface, not NADW, but IDW, extra old, nutrient-rich waters. So let's return to the Broken Ridge data and the Delta 13C and the Tasman leakage exploration here. And when we plot 754 MNSC on it, you see that it drops in concert with the Delta 13C. And so we're suggesting that another way of interpreting this record at the at the Broken Ridge at 7 million is to think about it in concert with IDW. And that IDW, what we may be looking at here is less of a massive plume of waters extending from the Arabian Sea to the Broken Ridge, but maybe instead an upwelling event and a productivity event that's associated with those very nutrient-rich IDW waters. Oh, something's just happened. I'm being annotated. So the take home is that what we're able to show with the Expedition 356 study is we were able to refine the timing of the shift to the North Pacific waters. We were able to confirm that tight relationship between the timing of the change in the Indian and the Australian climate. We're able to define the onset of modern Australian monsoon. That northward motion of Australia, in addition to driving the aridity that we describe in 356, created the conditions for the formation of the intermediate limb of thermohaline circulation and a second site of exchange between the Pacific and the Indian. It invigorated circulation in the Indian Ocean and may provide an alternative explanation for OMZ conditions at Broken Ridge. And the biggest take home is we need more core. So to this end, we have submitted a pre-proposal. Unfortunately, it was not supported, and so we're going to be revising it. But the idea is to try and get core that will give us the orbital resolution necessary to compare what's going on in these locations with the Antarctic at high resolution. And it's an opportunity then to really track what's going on with the Antarctic ice sheet without that bothersome IRD. Similarly, we put in a pre-proposal that also needs to be revised for drilling on the southwestern Indian margin up in the Arabian Sea, in addition to supporting the original objectives of that proposal. This will also allow us, because it'll be high resolution core, to answer some questions about erosion associated with the Tasman leakage onset, as well as the OMC at Broken Ridge. And then finally, we have put together, Gerald Auer has led this, a workshop to do some of these revisions, to synthesize a lot of our next steps into proposals. This is the website. I think many of you have gotten the announcement, and the flyer came along with Peter's announcement about this talk. And of course, it's an opportunity not only to write proposals, but to close the loop on the Asian-Australian monsoon system. I've squeezed a lot of references into one page, so folks can come back and pursue that, but that's the end of the talk. So happy to answer any questions.
Thank you very much, Beth. We do have a question. Mark Yu, would you like to ask a question?
Hi, Professor. So my question is, where do you think the IDW upwelling is coming from? Southern Ocean, or is it more north?
Yeah, I'm not sure. There's a lot of uncertainty about the position of the subtropical front and what exactly is happening in that zone. But the IDW supplies the surface waters. And so, you know, if the subtropical front of the AAC is expanded at that point, that allows for upwelling associated with that circulation closer to the Broken Ridge. I'm not really 100% sure how the Tasman leakage plays into that either.
Yeah, thanks. I'm just interested in looking at delta C13 minima between glacial and interglacial timescales, and I'm just thinking a lot of the sources are from the Southern Ocean, but maybe we could, maybe there could be other places to drill.
Yeah, you know, I think one of the advantages of the Broken Ridge is it's shallow. It's about 1,000 to 2,000 meters, depending on where you are, but it's open ocean. All of the sites that have been drilled, pretty much all of the sites in IODP2 are continental margin sites. And so the records aren't always as easy to and as clean to interpret because you have all of that continental input. This location, ostensibly, we would be able to pull an AAIW signal, a northern, maybe Banda intermediate, whatever you want to call it, waters, as well as Tasman leakage.
So, Beth, I'd like to ask a question. So you were teasing us at the beginning in your title about Asia and Australia and so on. But so I was wondering, do you think there's any linkage between these events you've been reconstructing for the Australian monsoon and things that we see in Asia, or are these two systems really evolving sort of independently of one another?
Yeah, you know, I think this is the thing that I think we really have to understand. At 7 million, we see so much change all around the basin. And so, you know, these are not deep water sites. These are generally intermediate water sites. And so I think that's probably the key to really understanding the connection to the Asian monsoon, especially the.
So essentially through changing the temperature of the Indian Ocean.
Yeah, I think so. I think so. No, we haven't really thought that much about, or yet, about these interactions, but there's got to be an enormous impact when you turn on an entire intermediate water limb of exchange between the Pacific and the Indian.
And so, I mean, if nobody else wants to ask a question, I've got another one. I was curious about your potassium humidity proxy, that potassium is going up when it's humid. Right? I always think of humid conditions leaching away potassium. Oh, could you walk me through that again rather quickly?
Yeah, we're using that potassium as a straight up measure of illite and illite production, right? So
Okay.
got a really high abundance of illite, weight percent, during those intervals when potassium is highest.
Okay. Were you ever worried about things like drainage reorganization in Australia, changing the signal at a particular site? I mean, I know this isn't Southeast Asia, but I wondered if the signal might change at one site in a way that's essentially not just related to the environment on shore. Or do you feel like you've got that spread of sites that gives you the coverage?
Yeah, well, for one thing, it's not that long, and we don't have evidence. Well, a couple of things. When you look at the regional geology, and you step a little bit deeper into the continent, the precipitation and the humidity changes that we're seeing are concordant with things that have been recorded around Australia. So I didn't include that in this talk to save time, but Snyderman has been looking at pollen records, and there's a long history of records for other parts of Australia that support the same kind of timing. It's just that we've never had the continuous record that we have from 356 that allows us to say this is when it happened. Snyderman's work is really important, but it's only in pieces.
Thank you. Does anyone else wish to ask a question? I'm going once, going twice. So in this case, we will wrap this seminar up. Maybe you all can either unmute or you can use the reaction button to express your appreciation for the talk. But thank you very much. And if you want to listen to this again, you can go on YouTube and look at it there. But thank you very much. So come back next week. Remember, the time of the talk is different next week. It's Schedule B. And you can look that up on the website, or you can, if you're not getting emails from me, I will send an email to people telling them when and how to connect to next week's talk. But if you haven't been getting the emails, send me an email at pclift@lsu.edu, and I will add you to the mailing list. Thank you very much.
Thanks, Beth. That was terrific.
Welcome. Thanks.
Thanks, Beth. I loved your analogies too. That was great.